Okay friends, in this lecture we are going to cover a very important topic of linear algebra, and this topic is eigenvalues and eigenvectors of a given matrix. The moment we are talking about eigenvalues and eigenvector of a matrix, then first of all you must know that we are talking about only for a square matrix. A square matrix means number of rows is equal to number of columns in that matrix. If the matrix is not a square matrix, then we cannot talk about its eigenvalues and eigenvectors. Therefore, first of all we are going to consider that the given matrix is a square matrix. Then what is the meaning of eigenvalues and eigenvector of such a square matrix? So, let us try to understand the meaning of eigenvalues and eigenvector. So, first step is that A is given to be a square matrix. Then a scalar valued number lambda is called eigenvalues of A if, or in fact if and only if there exists a non-zero x. This non-zero x is very important, non-zero x such that A x is equal to lambda x. Look at here, such that A x is equal to lambda x. What is the meaning of this? A is a square matrix. Suppose A is square matrix of order n by n. Then x is also a matrix of order n by 1, which is unknown. And if x is equal to lambda x, look at here, x is equal to lambda x, we can write this equation in the form of, look at here, A minus lambda I into x is equal to 0. We can write this one, that is Ax minus lambda x is equal to 0. When Ax minus lambda x is 0, this is same as A minus lambda I x is 0, where what is I? I is the identity matrix, and the order of I is same as that of A. If A is n by n square matrix, then I is also an identity matrix of order n by n. So, A minus lambda I x is equal to 0. So, this is linear and homogeneous equation, and this x has to, look at here, the moment it is linear and homogeneous, x is equal to 0 is always a solution. X is equal to 0 is always a solution. So, is there any solution? We are talking about x different from 0. Remember, this is very important, x is different from 0. Means, is there any solution of this equation A minus lambda I x is equal to 0? Is there any non-zero solution for this equation or no, for a given value of lambda? If yes, if there exists a non-zero solution x for a particular value of lambda, then that lambda is called eigenvalue of the matrix, and that corresponding non-zero solution x is called eigenvector. Is it clear? See once more, lambda is called an eigenvalue of the matrix A if this equation A minus lambda x is equal to 0 has a non-trivial solution, and that non-trivial solution means non-zero solution. So, that non-zero solution x is called eigenvector corresponding to the eigenvalue lambda. I believe that the idea of this eigenvalue and eigenvector, by this time it should be clear. At the same time, see that by definition itself, x, which is, if it is an eigenvector, it has to be different from 0. So, by definition eigenvector is always non-zero. We are looking for a solution of this equation A minus lambda x is equal to 0 for a non-zero solution, and that non-zero solution for corresponding to lambda is called eigenvector. So, x is always non-zero. Of course, x is equal to 0 is always a solution, but that solution is not of our interest if we are looking for an eigenvector. And therefore, this eigenvector is never 0 by definition itself. However, lambda equals 0 is permitted. Eigenvalue may be 0, but eigenvector is never 0. That is the first important remark. If you see several books on linear algebra, they call some authors call eigenvalue as characteristic value also or proper value also, and eigenvector is characteristic vector or proper vector. But in this course we shall always refer as eigenvalue and eigenvector. So, third remark is also very important. Look at here, if lambda is an eigenvalue, one eigenvalue, and corresponding to lambda x is an eigenvector, then whether this x which is an eigenvector, it is a unique eigenvector corresponding to a unique eigenvalue or no. Look at here, lambda is fixed, lambda is equal to some lambda 1 it is given, then corresponding to this lambda equals lambda 1, how many eigenvectors we will have? Answer is that we will have infinite number of eigenvectors. So, what is the meaning of infinite number of eigenvectors? Look at here, see again previous slides, we are looking for the solution of a minus lambda I x is equal to 0. So, x is equal to non-zero, it is if it is a solution of this equation, a minus lambda I into x is equal to 0. If x is equal to 0, it is a non-zero solution of this equation for a particular value of lambda, then that non-zero x is called eigenvector. And what is this x? X is a solution of this linear and homogeneous equation. And what I am saying, that even for lambda is unique, if then corresponding to one value of lambda, we will get not only one non-zero solution, we will get infinite number of solutions. What is the meaning of this? It means that corresponding to one eigenvalue we will get infinite number of eigenvectors. And what are those eigenvectors? Those eigenvectors are in fact, if x is an eigenvector, then you multiply x by any non-zero number, by any non-zero scalar. Suppose c non-zero scalar, then c into x is also an eigenvector. The moment x is an eigenvector, c into x is also an eigenvector for every non-zero c. So, whatever suppose x is an eigenvector, so 2 into x is an eigenvector, 3 into x is an eigenvector, 4 into x is an eigenvector, 0.56 into x is an eigenvector, 1 by 4th into x is an eigenvector, and so on and so forth. So, therefore, if x is an eigenvector corresponding to lambda, then c into x is also an eigenvector corresponding to lambda for every non-zero c. So, that is third remark, that is also very equally important. So, proof is very simple in fact. Suppose x is an eigenvector corresponding to lambda, therefore, by definition a x will be equal to lambda x. Okay. And what is the previous remark? That if x is an eigenvector, then y into cx is also an eigenvector for every non-zero c. So, see, calculate it, if y is equal to cx, if y is equal to cx, it is also an eigenvector for every non-zero c. It means what? We must be able to show that a y must be equal to lambda y. The moment we can prove that a y is equal to lambda y, this will imply that y is also an eigenvector, where y is equal to cx and x is already an eigenvector. So, if x is an eigenvector, therefore, x is equal to lambda x. Now, calculate a y is equal to and y is your cx. So, substitute a y, y is equal to cx, c is non-zero scalar, you can take it out. So, c into ax, then ax is again lambda x from the first equation, therefore, c into lambda x, again lambda you can take out. So, lambda into cx and cx is your y, cx is your y. So, this is your lambda y. So, see that we have proved that a y is equal to lambda y. So, therefore, a y is equal to lambda y, it implies that y is also an eigenvector of the matrix A corresponding to the eigenvalue lambda, and y is your cx, where c is non-zero. So, this shows that for one eigenvalue we will have infinite number of eigenvectors. This what we have seen remark 4, that ax is equal to lambda x can be written in the fashion of a minus lambda I x is equal to 0, where I is the identity matrix and the order of I is same as that of A. Look at here. Now, we have seen that number of eigenvectors corresponding to one eigenvalue will be infinite, and this set of non-zero solution of equation 1, the set of non-zero solutions of equation 1 is the set of all eigenvectors. So, eigenvectors is non-zero solution of equation 1, simple meaning. Non-zero solution of equation 1 are called eigenvectors of the matrix A corresponding to the eigenvalue lambda. And then see second word we are using, we are going to use what is the meaning of eigenspace. Eigenspace of the matrix A. Eigenspace means set of all possible solutions of the equation 1. Set of all possible solutions of equation 1 is called eigenspace of the matrix A. Remember here, set of all possible solutions, and this equation, first equation, A minus lambda x is equal to 0, x is equal to 0 is always a solution, and means what? So, eigenspace means 0 solution is also included, set of all solutions including 0 solutions of this equation 1 is called eigenspace. And what is the all possible solutions of A minus lambda x is equal to 0? Do you recall what is the meaning of null space of the matrix or null space of the linear transformation? Exactly, it is similar. Null space of the linear transformation T is the set of all points x from the domain space which are mapped on the 0 element of the range space. So, set of all x such that T of x is 0. So, solution of all possible solutions of T x is equal to 0. Exactly in a similar way, eigenspace means all possible solutions of equation A minus lambda x is equal to 0. So, therefore, eigenspace of A corresponding to A means null space of A minus lambda I, null space of A minus lambda I, that is kernel of A minus lambda I. This is same as the set of all solutions of x such that A minus lambda I x is equal to 0. And then what is the set of eigenvectors? Set of eigenvectors means from the eigenspace, look at here, eigenspace includes all possible solutions of equation 1 including 0 solution, and therefore from eigenspace if you remove the 0 solution, whatever it will be left, that will be called the set of all possible eigenvectors. Therefore, what is set of eigenvectors corresponding to lambda? That is the null space of A minus lambda I. Null space of A minus lambda I is the eigenspace of A minus the 0 solution, remove the 0 solution from the eigenspace, that is called, whatever it is left, that is called set of eigenvectors. Look at this result is very important and it is used, and it is trivial in fact, that suppose A is a square matrix, then these 3 statements are equivalent. Means if lambda, what is the meaning of these 3 statements are equivalent? Means lambda is an eigenvalue of A if and only if A minus lambda is singular, if and only if determinant of A minus lambda I is equal to 0. Look at here, why? What is the meaning? Lambda is an eigenvalue of A, the meaning thereby that A minus lambda I x is equal to 0, where x is different from 0. So, lambda is an eigenvalue of A, means it will satisfy this equation A minus lambda x is equal to 0 for non-zero x, and that non-zero x is called eigenvector of A corresponding to lambda. Look at here, this equation A minus lambda x is equal to 0, this equation it should have non-trivial solution, that is non-zero solution. When it will have non-zero solution? This will have non-zero solution if and only if this matrix A minus lambda I, this matrix is singular. The moment it is non-singular, the moment A minus lambda I is non-singular, means that the moment A minus lambda is invertible, then x is equal to 0 is the only solution, there is no any other solution except the 0 solution, and therefore, we cannot find any eigenvalue. What is the meaning we cannot find any eigenvalue? Does not mean that only lambda equals 0 will be an eigenvalue. We shall see in a short while. The moment A is an singular matrix, then lambda equals 0 is an eigenvalue. So, look at here, the A minus lambda x is equal to 0, we are looking for a non-trivial solution of this equation, and this equation will have non-trivial solution in x, that is non-zero solution in x, if and only if A minus lambda I is a singular matrix. If A minus lambda I is non-singular, that is if A minus lambda I is invertible, then x is equal to 0 is the only solution. Therefore, there is no eigenvector and eigenvalue in this case. Remember here, when A minus lambda I is non-singular, then x is equal to 0 is the only solution, therefore, no eigenvalue and no eigenvector. And for a non-zero solution in x, A minus lambda I must be singular. When A minus lambda is singular, means determinant of A minus lambda is equal to 0. These three statements are equivalent, means if and only if. So, therefore, if you want to find if matrix A is given, and then you want to show that, or if you want to find what is the eigenvalue of this matrix A, then just you find what is the determinant of A minus lambda I is equal to 0. This will be a polynomial equation. If A is a square matrix of order n, then this will be a polynomial in degree n. Then find the roots of this equation. The roots of this equation will give you the eigenvalues of this matrix A. But before going to give some example how to calculate eigenvalues and eigenvector, let us see few important results. As I have told you, this remark, first remark I have already discussed, that if A is a square matrix of order n by n, and we wish to find eigenvalue of this matrix A, then find first of all what is determinant of A minus lambda I, make it equal to 0. So, determinant of A minus lambda I is equal to 0, this equation is called characteristic equation, and determinant of A minus lambda I is called characteristic polynomial. So, determinant of A minus lambda I is called characteristic polynomial, and if you make it equal to 0, then it is called characteristic equation. And when it is a characteristic equation, and if A is a square matrix of order n, then this is a polynomial of degree n. When it is a polynomial of degree n, it will have n roots. These roots need not be, all roots need not be distinct, but will have n roots, and these roots are the values of lambda, and these are the values of the eigenvalues of the given matrix A. Look at your second remark, is saying that if lambda equals 0 is an eigenvalue of A if and only if A is singular. Before this one, I will have to go to the previous slide. Look at here. Remark 2 is saying that lambda equals 0 from this theorem. Lambda equals 0, it is an eigenvalue of A if and only if A is singular. It means what? Look at here. A minus lambda equals 0. The moment we are putting here lambda equals 0 is an eigenvalue of A. So, put here lambda equals 0, then what we are going to get? We are going to get here that determinant of A is equal to 0. And what is the meaning that determinant of A is 0? Means A is singular. Okay. So, lambda equals 0 is an eigenvalue of A if and only if A is a singular matrix. Therefore, it also follows that A is non-singular if and only if A does not have any 0 eigenvalue. Does not have any 0 eigenvalue means A has all non-zero eigenvalues. So, A is non-singular if and only if A has all non-zero eigenvalues. If there is any eigenvalue which is 0, A will be singular. So, this result is very important, that if lambda equals 0 is coming to be an eigenvalue, it will imply immediately that A is a singular matrix. And if all eigenvalues are non-zero, it will imply immediately that A is non-singular. And this is also a very important criteria how to find determinant of the matrix if you know all eigenvalues. Okay. So, suppose that lambda 1, lambda 2, lambda n, these are n eigenvalues. Some of the eigenvalues may be repeated also, some of the eigenvalues may be equal also, they need not be distinct, then determinant of the matrix is the product of n eigenvalues lambda 1 into lambda 2 into lambda n. So, if you know all eigenvalues of a given matrix A, therefore, you know the determinant of the matrix also. Determinant of the matrix, just to multiply all eigenvalues, you will get the determinant of the matrix. And it is obvious, because if lambda 1, lambda 2, lambda n, they are eigenvalues, then determinant of A minus lambda I can be written in this fashion. Why? Because suppose P x is a polynomial. Okay, P x is a polynomial of degree 3, I am saying P x is a polynomial of degree 3 and x is equal to 1, it is a root of this. If x is equal to 1 is a root of this, means x minus 1 is a factor of P x, x minus 1 is a factor of P x. Therefore, if determinant of A minus lambda I, it is a polynomial of degree n, and lambda 1, lambda 2, lambda n, they are roots of this characteristic equation, they are the roots of this equation, determinant of A minus lambda is equal to 0. Therefore, determinant of A minus lambda I must be written as lambda 1 minus lambda into lambda 2 minus lambda and so on so forth into lambda n minus lambda. It means what? Lambda 1 minus excuse me. It simply say that lambda 1 minus lambda is a factor of determinant of A minus lambda I. Lambda 2 minus lambda, it is also a factor of determinant of A minus lambda I, and so on and so forth. And if you substitute lambda equals 0, substitute lambda equals 0 in this equation, we are going to get that determinant of A is equal to lambda 1 into lambda 2 into lambda 3 and so on and so forth into lambda n. So, this is also a very useful technique to find determinant of the matrix by knowing the eigenvalues of the matrix. Another also very important remark, that if lambda is an eigenvalue of A, then lambda square will be an eigenvalue of A square, lambda q will be an eigenvalue of A q, and so on and so forth. Lambda to the power n is an eigenvalue of A to the power n. This is also used frequently. So, suppose for example, if lambda is an eigenvalue of A, then A x is equal to lambda x for non-zero x. This is just by definition. Then what is the meaning of A square x? A square x is A of A x, and A x is your lambda x, and then lambda you take it out because it is scalar. So, this is lambda of A x, and A x is equal to lambda x from this equation. So, this is lambda into lambda x, this is lambda square x. So, what we have shown, that if A x is equal to lambda x, then A square x is equal to lambda square x from here. Just again you can multiply by A on both sides, then you can see that A q x is equal to lambda q x, A 4 x is equal to lambda to the power 4 x. This means that lambda to the power n is an eigenvalue of A to the power n, if lambda is an eigenvalue of A. So, remember that if you know the eigenvalue of A, therefore, you know the eigenvalue of A square also, A q also, A to the power 4 also, and so on and so forth, you know the eigenvalue of lambda to the power n. Just by knowing the eigenvalue of A, we can calculate immediately the eigenvalues of A to the power n. This result is also a very important result, that is known as Cayley-Hamilton theorem. Cayley-Hamilton theorem, it states that every square matrix satisfies its own characteristic polynomial. Every square matrix satisfies its own characteristic polynomial. I have defined what is the meaning of characteristic polynomial. Characteristic polynomial is determinant of A minus lambda I, that is your characteristic polynomial. And if A is a square matrix of order n, then this characteristic polynomial is a polynomial of degree n. Okay. And that we are calling let A be a square matrix of order n, and P lambda is equal to this. Okay. So, P lambda is the characteristic polynomial, it is a polynomial of degree n, polynomial in lambda. And then Cayley-Hamilton theorem tells that every square matrix will satisfy its own characteristic polynomial. Means what? That if you replace lambda by A, then P of A will be 0. So, P of A is 0. So, this P of A means a to the power n plus n minus 1 into a to the power n minus 1 and so on and so forth, plus a 1 into a plus a 0 must be equal to 0. So, P a is equal to 0. So, this is also a very important result, that you are supposed to know that what is Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic polynomial. Now, let us start theory part. We have seen, let us start some problems, that if a matrix is given, then how to calculate eigenvalues and all eigenvectors, or how to calculate eigenvalues and the eigenspace. If we know the eigenspace, from the eigenspace just to remove the 0 solution, that whatever it is left we will get the set of all possible eigenvectors. And how to get all possible eigenvectors? If you know one eigenvector, then scalar multiple of that is also an eigenvector. And what is the meaning of scalar multiple? If x is an eigenvector, then c into x is also an eigenvector. And what is this c into x? Scalar multiple of x, that is the span of x, we shall see in a short while. Suppose this matrix is given with us, A is equal to 2 by 2 matrix, a very simple 2 by 2 matrix. Let us start with 2 by 2, then we shall go 3 by 3. And we want to find all eigenvalues and all eigenvectors corresponding to these eigenvalues. So, as I told you that if you want to calculate all possible eigenvalues, then first step is that calculate the characteristic equation determinant of A minus lambda I. A minus lambda I. So, first you calculate what is A minus lambda I. A minus lambda I. Remember here, A is a matrix of order 2 by 2. Therefore, I is also an identity matrix of order 2 by 2. Identity matrix means all principal diagonal elements are 1 and other elements are 0. So, it means what? A minus lambda I. So, it means what? From the matrix A, this from the diagonal elements we shall subtract lambda, and then see what is the determinant of this one. This is equal to 0, determinant of this one is 0. So, that will give you the characteristic equation. So, let us see what is this one. If lambda is an eigenvalue of A, then look at here, this is determinant of A minus lambda I, this is equal to 0. So, this is our characteristic equation. And from here, just to see how you know at this stage how to calculate this determinant. So, this into this 7 minus lambda multiplied by minus 1 minus lambda, and then minus of minus 3 into 4 minus 12. So, that is plus 12 is equal to 0. Simplify, you are going to get this equation. Look at here, A j matrix of order 2 by 2. So, you are going to get this is a characteristic polynomial of degree 2, lambda square minus 6 lambda plus 5 is equal to 0. It is a characteristic polynomial of degree 2. So, see what are the values of lambda. Lambda equals 1 and 5, these are the roots of this equation, and these roots are called eigenvalues of the matrix A. So, therefore, lambda equals 1 and lambda equals 5, these are eigenvalues of the given matrix A. So, first step is our, we know eigenvalues. Second step is very important. What is second step? Calculate eigenspace corresponding to lambda equals 1 and eigenspace corresponding to lambda equals 5. If we know eigenspace, then we know all possible eigenvectors. So, let us see that step little slowly. So, now lambda equals 1 and lambda equals 5. We are going to find second step, that find eigenspace corresponding to lambda equals 1. And we have seen what is the meaning of eigenspace. Null space of A minus lambda I, null space of A minus lambda I. And what is null space of A minus lambda I? This is the set of all those x such that A minus lambda x is equal to 0. Remember here, we are going to solve an equation of the type A minus lambda x is equal to 0. All possible solutions including the 0 solutions. So, the set of all solutions is called null space of A minus lambda I here. Set of all solutions of A minus lambda x is equal to 0 is called null space of A minus lambda I, and null space of A minus lambda I is called eigenspace of the matrix A corresponding to the eigenvalue lambda. So, lambda equals 1. So, substitute lambda equals 1. Lambda equals 1 means null space of A minus I, lambda equals 1. So, A minus I x is equal to 0, A minus I x is equal to 0. See what is A minus I x is equal to 0? A minus I. So, A minus I is 6 4 minus 3 2. From the given matrix A, remove minus I, remove identity matrix. Remove identity matrix means from the diagonal elements remove or subtract 1. So, diagonal element earlier it was 7 and minus 1. Look at here, 7 and minus 1. Diagonal elements are 7 and minus 1. So, A minus lambda I, what is the meaning of A minus lambda I then? 7 minus 1, here minus 1 minus 1. That is the only difference. So, this is your 6 4 minus 3 2 x 1 x 2, this is equal to 0. So, let us see, this is in fact 6 into x 1 plus 4 into x 2 is equal to 0, and second one is minus 3 into x 1 minus 2 into x 2 is equal to 0. And see that both equations are same, there is no difference, both equations are coinciding with each other. So, if you combine these two equations, we are going to get simply 3 x 1 plus 2 x 2 is equal to 0. This simply tells us that 3 x 1 plus 2 x 2 is 0, and therefore, you can write here x 1 is equal to minus 2 by 3 x 2. Remember, x 1 x 2 is a solution and we are looking for a non-zero solution. So, x 2 is, look at it, x 1 is equal to minus 2 by 3 into x 2, where x 2 is any real number. X 2 is this is called free variable. So, whatever the value of x 2 you are going to calculate, give, accordingly x 1 will be calculated. Okay. Suppose x 2 is equal to, we are giving here 3, x 2 is equal to, suppose I am putting here 3. Therefore, what is x 1? X 1 is your minus 2. So, x 1 is minus 2 and x 2 is 3, it is a non-zero solution. So, minus 2 3, it is a non-zero solution. Therefore, any scalar multiple of this will be also a solution, and that is called the span of A minus I. Span of span of A minus I. Look at here, first of all, null space of A minus lambda I, lambda is 1 in this case, therefore, null space of A minus I, this is the set of all points x is equal to x 1 x 2, where x 1 is calculated to be minus 2 by 3 and x 2 is any real number. Now, x 2 it is your choice, give assign any real number. So, suppose in this case I am assigning here x 2 is equal to 1, then x 2 substitute x 1 is equal to minus 2 by 3 first of all, then x 2 take out. So, look at here, we are going to get minus 2 by 3, minus 2 by 3 1. So, when it is minus 2 by 3 1, then multiplied by x 2 means what? All null space of A minus I is a scalar multiple of minus 2 by 3 1, and scalar multiple of minus 2 by 3 I is same as the scalar multiple of minus 2 3, as I have told you, seen here that substitute x 2 is equal to 3, will get here x 1 is equal to minus 2, x 1 is equal to minus 2. So, therefore, minus 2 and 3, it is also a non-zero solution. You can multiply here by 3 and then see that you will get another scalar alpha. I am multiplying here by 3. So, 3 x 2, that is your alpha, this is your minus 2 3. So, all solutions are scalar multiple of minus 2 3, and what is the meaning of all is scalar multiples of minus 2 3? That is the span of the set consisting of one vector minus 2 3. So, that is called span of this. Remember here 0 0, it is also included here, 0 0 is also a solution, because if you take x 2 is equal to 0, x 1 will be 0. So, 0 0 is also a solution. So, for eigenspace we will have to include 0 solution also, because eigenspace is the set of all possible solutions including 0 solutions. Therefore, span of minus 2 3 is the eigenspace, that is the null space of A minus I. And if from this eigenspace, that is from this span of minus 2 3, if you remove the vector 0 0, then you will get set of all possible eigenvectors. So, now we have seen that null space of A minus I is span of the vector minus 2 3, and set of all possible eigenvectors corresponding to lambda is equal to 1 is this span of minus 2 3 minus the 0 solution 0 0. So, this will give the set of all possible eigenvectors. So, minus 2 3 is one eigenvector, multiply by it any non-zero quantity, will get another eigenvector. Okay. So, there we have seen what is the eigenspace and set of all eigenvectors corresponding to eigenvalue lambda equals 1, but we have seen that lambda equals 5 is also an eigenvalue of the given matrix A. So, in the second stage we shall calculate exactly in a similar way what are the eigenspace or what is the eigenspace and what are all possible eigenvectors corresponding to lambda is equal to 5. So, let us see third step, we are having lambda equals 5 is an eigenvalue, then calculate what is null space of A minus lambda I, lambda is equal to 5, null space of A minus 5 I, and therefore, this is the set of all those x where A minus 5 I x is equal to 0. So, calculate A minus 5 I first of all, minus 5 I. So, 5 from the diagonal element subtract 5, you are going to get here 2 and minus 6, see that this is the matrix A minus 5 I, A minus 5 I x is equal to 0, and from here you see that 2 into x 1 plus 4 into x 2 is 0, and from minus 3 into x 1 minus 6 into x 2 is again 0. So, this shows that x 1 is equal to minus 2 x 2, and where x 2 is again any free variable, x 2 is any real number. Therefore, again we are going to get infinite number of solutions. So, let us see finally what are all those possible solutions. One choice is that take x 2 is equal to 1, take here x 2 is equal to 1, then you see that x 1 we are going to get is minus 2. So, minus 2 x 1 is equal to minus 2 and x 2 is equal to 1, that is minus 2 1 is one eigenvector, that is a non-zero solution. Okay. And all other solutions will be scalar multiple of this. Therefore, null space of A minus 5 I is the set of all x 1 x 2 where x 1 is minus 2 x 2 and x 2 is any real number. Substitute the value of x 1 is equal to minus 2 x 2 here, again x 2 we can take it out. So, see that this is x 2 into minus 2 1. So, all solutions are the scalar multiple of minus 2 1, and all scalar multiple of minus 2 1 means it is the span of minus 2 1, and span of minus 2 1, this is your eigenspace for lambda equals 5. And therefore, from this eigenspace you remove this 0 solution, you will get the set of all possible eigenvectors. Let us see one more example of 3 by 3 matrix. So, here A is given to be a 3 by 3 matrix, we are interested to know all possible eigenvalues and the corresponding eigenspace and set of eigenvectors. See that I have written here directly lambda equals 0, 1, 2 are eigenvalues of A, but how? You can see from the next slide that if you want to calculate, if lambda is an eigenvalue of A, then again determinant of A minus lambda I must be equal to 0. And what is determinant of A minus lambda I? This is your determinant of A minus lambda I. From the diagonal element remove or subtract lambda, this is equal to 0. This is our characteristic equation. A is a order of matrix 3 by 3, therefore, you are going to get a polynomial of degree 3. So, look at here determinant 1 minus lambda into this quantity. So, see from here that lambda equals 0, lambda equals 1, lambda equals 2, these are the roots of this equation, this characteristic equation, and therefore, these are the eigenvalues of the matrix A. Now, we will have 3 cases here. What are the all possible eigenvectors corresponding to lambda equals 0, 1 and 2. So, we shall find it out all eigenspaces corresponding to lambda equals 0, lambda equals 1 and lambda equals 2, and from there we shall remove the 0 solution, we will get set of all eigenvectors. Now, lambda equals 0 is one eigenvalue, so we are going to find eigenspace for lambda equals 0. For eigenspace lambda equals 0 means null space of A minus lambda I, and lambda is 0, therefore, null space of A. Null space of A means set of all those x where A x is equal to 0, A x is equal to 0, A of x is equal to 0. Okay. So, how to solve equation A x is equal to 0? This is 3 by 3 matrix. So, see this B is your augmented matrix, you are aware of by this time what is your augmented matrix, this is B is your augmented matrix, that is this is the coefficient matrix of A, this is the coefficient matrix of A, and this one, this part is 0 0 0, the last column is x equal to 0, that is the 0 matrix. And from here you see that from here again what I have done here, R3 has been replaced by R3 minus R2. R3 means row 3, R3 has been replaced by R3 minus R2, R3 minus R2, see that you are going to get 0, 0, 0. So, what we are going to get from this equation? 0 into x1 plus 0 into x2 plus 0 into x3 is equal to 0. From the second equation, from here we will get 0 into x1 plus 1 into x2 plus 1 into x3 is equal to 0. And the first equation is 1 into x1 plus 0 into x2 plus 0 into x3 is equal to 0. So, that is x1 is 0. So, from here let us see what we are going to get. We are getting here what we are getting here. First of all, we are getting that x1 is 0. So, x1 is always 0. After that, x2 plus x3 is 0, and therefore, x2 is minus x3, and x3 is free variable, x3 is any real number. So, see here that we are going to get infinite number of solutions. If you assign any x3, if you are assigning any x3, then corresponding to that you will get x2, and x1 is always 0. So, we will get infinite number of solutions. See what are those solutions, and those solutions will be called, of course, including the 0 solution. So, we are going to write all possible solutions of this equation x1 is 0, x2 plus x3 is 0, and see that null space of A is the set of all triplets x1, x2, x3, where Ax is 0, and Ax is 0 means we have seen that x1 must be 0 and x2 is equal to minus x3. So, x1 is 0, x2 is equal to minus x3 we have substituted, and x3 is any real number. So, look at here 0 minus x3 and x3 we have taken out. So, what is left here? 0 minus 1 1, and x3 is any real number. So, what we are going to get here? This set null space of A, this is the scalar multiple of 0 minus 1 1, this factor 0 minus 1 and 1, and therefore, this is the span of 0 minus 1 1, this is the span of 0 minus 1 1, and this is called eigenspace corresponding to lambda equals 0. And from this eigenspace, look at here the 0 solution 0 0 0, that is x1 is 0, x2 is 0, x3 is 0, it has been removed, and whatever it is left, that is called the set of all eigenvectors. Therefore, set of all eigenvectors corresponding to lambda equals 0 is this one. Therefore, 0 minus 1 1 is one eigenvector, and any non-zero scalar multiple of this is also an eigenvector. If you look at here, lambda equals 1 is also an eigenvalue. If lambda equals 1 an eigenvalue, let us see how to find eigenspace corresponding to lambda equals 1. Lambda equals 1 means null space of A minus lambda I, lambda is 1. So, null space of A minus I. Null space of A minus I means set of all those x where A minus Ix is equal to 0. So, let us say solve A minus Ix is equal to 0, A minus I. So, what is this matrix be? This is the augmented matrix corresponding to A minus Ix is equal to 0, A minus Ix is equal to 0. So, from the matrix A, the identity matrix I has been subtracted, means that from the diagonal elements of the matrix A, 1 has been subtracted, and whatever it is left, this is the matrix up to here, this is the matrix A minus I, and this is 0 0 is because of this 0 augmented matrix. And see what is the meaning of this one. From the first equation I am getting here 0 0 0 is equal to 0, so no problem at all. From second one is 0 into x1 plus 0 into x2 plus 1 into x3 is equal to 0. So, therefore, x3 is always 0. And what is the last equation? 0 into x1 plus 1 into x2 plus 0 into x3 is equal to 0. So, therefore, x2 is 0. So, x2 is 0 and x3 is 0. x2 and x3 are always 0, and there is no restriction on x1. x1 is a free variable. x1 is a free variable. There is no restriction on x1. x1 is any real number, but x2 and x3 has to be 0. So, if x1 is any real number, so take x1 is equal to 1. So, 1 0 0, it is one eigenvector. So, any scalar multiple of that will be an eigenvector. So, 2 0 0, 3 0 0, 4 0 0, it is also an eigenvector. And therefore, let us see how we are going to write eigenspace in the terms of span. Therefore, null space of A minus I is the set of all triplets x1, x2, x3, where x2 and x3 both are 0, and xy is any arbitrary real number, x1 is arbitrary real number, x1 is, see, I am taking out 1. So, therefore, this set is the all possible scalar multiples of 1 0 0. So, therefore, span of 1 0 0, span of 1 0 0, it is the eigenspace corresponding to lambda equals 1. And set of eigenvectors, see that from this span, from this eigenspace, this 0 solution has been removed, and whatever it is left, it is called the set of all possible eigenvectors corresponding to lambda equals 1. Just you can verify this one, that lambda equals 2, it is an lambda equals 2, it is also an eigenvalue of A. Therefore, see what is the null space of A minus 2I, you can see that it is here x1 is always 0 and x2 and x3 both are equal, and they are any real number, both are equal. This is also equally important, x2 and x3 both are equal and they are any real number. So, look at here, we can take here 0 1 1, span of 0 1 1, this is the eigenspace corresponding to lambda equals 2. We will have to, first of all, this part I am leaving an exercise, A minus lambda I, calculate what is the null space of A minus 2I, that is solve the equation A minus 2I x is equal to 0. This part, solution of A minus 2I into x is equal to 0, solve this equation. You will see that x1 is always 0 and x2 is equal to x3 and x3 is any real number, that is the solution. Therefore, eigenspace is span of 0 1 1, and set of eigenvectors is exactly similar. From eigenspace we are removing this 0 solution, and this is set of eigenvectors. Okay, thank you. This is all about the set eigenvalues and eigenvectors of a given matrix.